Okay, this is going to be the answer key for the energy pie graph practice. Um, so hopefully you guys got through this on your own. These sort of get progressively harder, and I saw a lot of good work happening yesterday when people were doing these. But I'm going to fill it in, and I'll explain it as I go. If you have questions on something that I do, make sure you raise your hand and get that answered right now. Okay, so for the first one, we see that this battery car is moving at a constant speed for the whole time. So it never slows down, it never speeds up, and it says ignore friction. So if I'm going to ignore friction and there's not going to be any thermal energy, that means that all of these are going to be all kinetic all the time. So I know some of you guys like filled everything in. For the sake of time, I'm not going to do that. I'm just going to leave it blank and check out this little trick. I'm just going to say that if the circle is blank, then that means it is EK, kinetic energy. All right, so it's kinetic energy all the time. It's moving, and that's the only type of energy that it has. Okay, so a tennis ball rolls across the floor with an initial velocity and comes to a stop. So at this point, the tennis ball is already moving. And all it does as it goes this way is it just slows down. Now, hopefully we know that the reason that it slows down, hang on, that's about to go out. Come back to life. All right, so hopefully we know that the reason that it slows down is because there's friction. So it's going to start off just like the car. It's going to start off with kinetic energy. So I'm going to leave, I'll light my key and I'll say when it's blank, then it is all kinetic energy. Now as it slows down, the friction is going to turn that kinetic energy, sorry for the buffering there, the friction is going to turn that kinetic energy into, we'll say shaded area is ET, or thermal energy. Hi, Abraham. Okay, so for the second ball, some of the energy has turned into thermal energy. So I still have a lot of kinetic, but I also have a little bit of thermal. Go ahead and sharpen your pencil, Abraham. Don't worry about the sound. Okay. Now for the third one, let's do even more of it. I know I saw some people do half. Let's do even more than half. And really, your proportions don't really matter, guys. As long as I can clearly see that it's going from more kinetic to more thermal. Okay? And then finally, when the ball comes to a stop, so remember this says comes to a stop, if this ball's not moving, then that means that it must be all thermal energy. Oh. Check this out. Well, Mr. McSparrow, gotta be smarter. Oh, look at that. Fill the whole thing in with thermal energy. Okay. Okay, so that's that one. We go from kinetic over here to thermal over here. Now the next one, energy pie graph sorry, I'm just reading the top. A pullback car starts pulled back, then speeds up when it's released. Okay, so if we think about the pullback car, if this is the point where it's pulled all the way back and it's not moving yet, that means that it has no kinetic energy, but all potential energy. Specifically, and we'll call that the white, okay? Specifically, it's going to be, okay? It's going to be elastic potential, okay? So it's potential energy, but it's still elastic. Now, as the car starts to speed up, for this second one, some of that elastic is going to turn into kinetic energy. So it starts to move. All right, so let's say that so half of it is elastic, and then the other half is kinetic, except for we're going to say a tiny little sliver because there's friction in this. So what does friction do? Well, friction, okay, friction, black, gives me thermal. So I'm going to have a bunch of kinetic, and then a tiny little bit of thermal. Okay, now over here. Once this thing is going full speed, there is no longer any elastic potential. The elastic is all gone. Now it's all kinetic except for I'm going to have a little bit more thermal as well. So let's draw my thermal first. So thermal, the longer it goes, the more thermal it has. So notice my slice of thermal here is bigger than my slice of thermal there. And then everything else is kinetic. So it's mostly kinetic with a little bit of thermal. Now, as we move on over here, as it slows down, a bigger chunk is going to be thermal, but it's still moving, so we still have some kinetic. So we'll call it like half and half kinetic and thermal. And at the very end, when it's stopped, it's going to be all thermal. Anytime an object slows down and stops because of friction, it ends with all thermal energy. Okay, close to done. All right, bungee jumper jumps off a bridge and reaches his lowest point. Okay, so if he is standing on top of a bridge and he's not moving anywhere, that means that he has all gravitational potential energy, EG. So right now I'm going to leave his circle white because he's all gravitational potential. Now once he jumps, he starts moving, which means he's going to need some kinetic energy. Okay. Now, his bungee cord hasn't started to stretch out yet, so there's no elastic yet, although there will be in the future. But right now, it's a mix of gravitational and kinetic. All right. Now at the end, when he's stretched all the way out, he's not moving anymore, so there's no more kinetic. He is as low as he's going to go, so there's no more gravitational. So the only thing left for him is elastic, and if you had elastic, leave it. Sorry, we'll go EL. So he's stretched all the way out. The only type of energy he has is elastic. There we go. So we go from gravitational potential and kinetic, and then elastic at the end when he stretches that band out because he's going to bounce back up. All right. Nice work.